Welcome back to the lecture series on analysis in state space. The topics for today's lecture are stability, controllability, and observability. Before moving on to today's topics, let us have a quick review of what we learned in the last two lectures. In the last two lectures, we saw how we can get the solution of state space model x dot of t is equal to a x of t plus b u of t. We found that the solution contains two parts, namely response due to the initial conditions and the response due to the input. Response due to the initial conditions is given by equation 1 and the response due to the input is given by equation 2. The total response is given by equation number 3. In all the equations, we assume that the start time of analysis is t0. But if we take the start time of analysis as 0 seconds, then the equations 1 to 3 become as given in equations 4 to 6. We call these equations as state transition equations. And the important term in these equations is e power at, which we represented it as phi of t. And we called it as the state transition matrix for obvious reasons. Also, we understood the properties of state transition matrix and how the state transition matrix and the solution of state equation can be evaluated using Laplace transform. Also, we used the above method to get the solution of state equation describing an armature controlled separately excited DC motor. For any system, we can find the state response, or we can find the response of the system in this manner, and we can calculate even the output. How we can calculate the output if we get x of t is, if we have x of t as a solution, the output can be written as y of t is equal to c x of t plus du of t. Since u of t is already known and x of t is now obtained as a solution of the state equation, we can find y of t. So therefore, using this x of t and y of t, I can get the complete response of the system. From x of t, I can plot x1 of t with respect to time to xn of t. Okay, maybe I'll get some responses like this. Also, from this y of t, I can plot y1 of t up to ym of t. Maybe some responses like this. So now looking at this responses, I can analyze the system. For example, whether I can analyze whether the system is going to be stable, then what is going to be the rise time, what is going to be the peak time, what is going to be the settling time, and all those stuff I can understand. Okay, so even if this analytical solution is not possible, I can get these plots by numerical integration of the state equation, and say once I get these responses, I can analyze the system. Especially, I can analyze the stability of the system by looking at the responses. So when I talk about the stability, we should know what is meant by stability of a system, or what is meant by stability analysis. When I say stability, I mean the bounded input, bounded output stability. So we call it as BIBO stability. What is meant by BI/BO stability? A system is said to be BI/BO stable or simply stable if the output y of t is bounded to a bounded input u of t. For example, if I take a step input, this step input is a bounded input. If I give this step input to a system, if I get a response y of t something like this, then I say the system is stable. For a bounded input, the output is bounded within some permissible limits, and therefore I call this as a stable system. But at the same time, for this bounded input, if I get something like this, then I call this system as unstable system, because for a bounded input, the output is not bounded within the permissible limits, and as time increases, y of t grows out of bounds, and therefore this system is not BI/BO stable, or simply the system is not stable. So therefore, what we have understood is, by plotting these responses, I can understand whether the system is stable or not. But getting these responses, it is not straightforward. Either I have to solve the system analytically and plot it, or I have to solve it numerically by integrating the state equation, and I have to plot it and I have to see. So the question is whether I can know the system is stable or not by looking at the system model itself. Okay, so if I can find this stability, if I can analyze the system for its stability using the model itself, then it is going to be an easier task. Yes, we can do this stability analysis by looking at the model itself. So in classical control theory, how we do this is, if I have a transfer function g of s, which will have a denominator polynomial and numerator polynomial, I will equate this denominator polynomial to 0, and this equation we call as the characteristic equation, and this root of this characteristics equations are called poles. Roots of this characteristic equations are called the poles of the system. If we plot the roots of the characteristic polynomial p of s equal to 0 on the complex plane, and these roots are what we call it as the poles. If I plot them in the complex plane, I get this pole 0 plot, and by looking at this pole 0 plot, I can say whether the system is stable or not. This is the left of plane and this is the right of plane. If all my poles are falling on the left of plane, then my system is stable. So to fall on the left of plane, all these poles should have a negative real part. Okay, so they can be real or complex in nature, whatever it may be, they should have a negative real part. If the poles are on the right of plane, then the system is unstable. That means if the poles have a positive real part, then the system is going to be unstable. If the poles are lying on the imaginary axis in the middle, then the system is marginally stable. So that is, the system is marginally stable for purely imaginary poles. Okay, this is what the stability analysis in classical control theory. But when it comes to the modern control theory, which uses the state space model, instead of this transfer function model, we have got x dot of t is equal to x plus vu. In the previous lectures, we have understood that the eigenvalues of the state matrix A are nothing but the poles of the system. Eigenvalues of A, the matrix A, and the poles of the system are one and the same. Therefore, when it comes to the state space model, how we can analyze the stability of a system is, again, if the eigenvalues are lying on the left of plane, the system is going to be stable. And if the eigenvalues are lying on the right of plane, the system is unstable. And if the eigenvalues are lying on the imaginary axis, then the system is marginally stable. Even if one of the system pole is on the right of plane, even then the system is unstable. For example, let us assume that there are 5 poles or 5 eigenvalues for a system, and out of the 5, 4 are lying on the left of plane and 1 pole is lying on the right of plane, or 1 pole is lying on the imaginary axis, then the system is not stable. For the system to be stable, all the poles have to be lying on the left of plane. Okay, so therefore, using state space model, how you can analyze the stability of the system is find out the eigenvalues of the state matrix A, and if they are lying on the left side, it is stable, otherwise it's not stable, and we can find out the stability by using this. But what if the system is not stable, or the system may be stable but the response is not as I expected? Here comes the controller into picture. What the controller does is, it manipulates the input to the system or plant so that it makes the unstable system as a stable system, or it makes the system to give a desired response as the output. So if I use a controller, the controller has to act on some input. How I derive is through an error signal obtained from the difference of the reference input and the feedback from this y of s or y of t. So this is how a controller is built into the system to control or to have some control over this output. The control law here is u of s is equal to r of s minus y of s into c of s, where c of s is the transfer function of the controller. Okay, so this is the error signal r of s minus y of s, that is multiplied by c of s, and that is available as the control input to the system. Now this input u, I will call it as a control input, and this is called as the reference input. Okay, and this is the feedback signal. Fine. We have heard about different kinds of controllers. Some of the controllers you might be familiar, or the PID controller or compensators, that is lead lag compensators. So they fall into this category. There is another way of manipulating this input also. In this, what we will do is, we will shift this controller from the forward path to the feedback path. I put the controller in the feedback path. And this also gives a manipulated input to the system or plant. The control law here is u of s is equal to r of s minus k into y of s. Usually this k will be a proportional controller with a constant gain k. This kind of control, I call it as the feedback control. Okay, so from the forward path control we have moved to the feedback control. Again, I'm talking about only the input and output, but if I change the system model to state space model, which is represented by x dot is equal to ax plus bu, of course everything is in time domain, therefore I have to change everything to time domain r of t, and this is also y of t. No, so this is not going to be y of t. Okay, so some output. So what is going to be what will be the output if this system is represented by this state equation? Then if I solve the state equation, what is going to be the output? So the state equation relates this input and the state variables x. Therefore, when I solve this equation, state equation, what I'll be getting here is the solution of the state equation, that is x of t. Okay. So many a times control of this state variables are also important, because let me take up an example. So the example what we took in the last lecture, that is an armature controlled separately excited DC motor. So the output there is the speed of the rotor, angular speed of the rotor, and apart from this angular speed, there is one more state variable, that is the IA, armature current. Let us assume that I am controlling the output, that is angular speed omega of t, but the armature current increases. I am not able to control armature current. What will happen? The motor gets damaged. Therefore, in most of the cases, in most of the systems, not only the output, but the internal state variables also have to be controlled. Okay, so therefore, instead of taking this y of t as the output of the entire system, we can take x of t as the output of the system, feed back this x of t, and we can control the x of t. Also, please notice that y of t, this output is given by c into x of t plus du of t. So therefore, if x of t is under control, then y of t is also controlled. Okay, so therefore, the objective of a system modeled in state space is to control all the state variables. So therefore, this system, I will call it as the state feedback control system. This is called a state feedback control. And the control law now is u of t is equal to r of t minus k into x of t. Okay. One important thing to be noted here is x of t is not a single variable. It contains x1 to xn, and therefore all the signals have to be fed back. And therefore, this k is no more a single constant, a scalar constant. It is going to be a matrix. The size of this k matrix will be r cross n. Okay, and this matrix is what we call it as state feedback gain matrix. This is what we call it as a state feedback gain matrix. Obviously, the u of t can be controlled by appropriately choosing the value of k. Okay. Now we will see how inclusion of this state feedback alters or modifies the location of poles and improves the performance of the system, because the ultimate purpose is to improve the system performance, and that has to be analyzed. This is the system without the state feedback, and the state matrix for this system is A. So its eigenvalues or input is u, and the eigenvalues can be obtained from this state matrix, and I will have a set of eigenvalues. Okay, So let us assume that this eigenvalues I'm not satisfied because maybe it is one of the eigenvalue is on the right side and the system is unstable or something. Now I have included a state feedback controller in the system, and let us see how this equation of the system is getting modified. So with this control, even with this control, the plant model is the same. Only thing is the input is get altered. Okay, so the input here is u of t is equal to r of t minus k into x of t. So if I substitute this becomes x dot is equal to ax plus b into r of t. Okay, so let me include x of t and t. Okay, r of t minus k into x of t. So this can be written as a x of t plus b r of t minus bk x of t. So this bk x of t and a x of t can be combined, and I get a new state equation a minus bk into x of t plus b r of t. Okay, if you look at this equation, it is very clear that this is also of the form x dot is equal to ax plus bu. Only thing is now the state matrix have changed from a to a minus bk, and the input is no more u, the input to the system is r of t. So this x dot is equal to ax plus bu represents this system. This equation x dot is equal to a minus bk into x plus b r of t represents this system. It is the same system, only thing is with this state feedback controller implemented in the system. So what is the advantage of changing the system matrix from a to a minus bk? Because so this becomes the new state matrix, and this state matrix will give me a entirely new set of eigenvalues, and if this k is appropriately chosen, then I can get the desired eigenvalue. So whatever eigenvalue I decide, so that the system is stable and the system performance is better than the previous system, I can choose an appropriate value of k here and I can get. This is what we call it as the pole placement problem or controller design, state feedback controller design problem. And this can be illustrated with the help of an example. And let us assume that this A and B are the matrices associated with this model. X dot is equal to Ax plus Bu. And if I take the eigenvalues for this state matrix, what I will be getting is 2 and minus 5. Obviously, minus 5 falls on the left side of the complex plane, but 2, since it has got a positive real part, it will fall on the right of the complex plane. So therefore, because of this particular eigenvalue, the system is going to be unstable. Now, let me design a state feedback controller for this, and assume that I got the state feedback controller gain matrix as 1, 4. So please note the controller gain matrix will be of the size R cross N. Here there is, let us assume that there is only one output, only one input. R is the number of inputs, and since the number of states is 2, so this K matrix will have the order of 1 cross 2. So with this K matrix, now the new state matrix for the system is A minus BK. So if I calculate A minus BK, this is what I will get. And for this state matrix, if I take the eigenvalues, both the eigenvalues are negative, So obviously, since both the eigenvalues fall on the left side of the complex plane, the system is going to be stable. So what we understand is by appropriately designing the state feedback controller, designing what I mean is choosing this K matrix values, I can change the unstable system into a stable system. Okay, or even if the system is stable, if the system performance is not as expected, I can change the system to give me a desired performance. Or otherwise, what I can say is this state feedback controller helps me to control the states, helps me to control all the states in the system so that the system is system output is bounded or within the required specifications. However, there are a few questions which arise in the design of this controller. There are two questions, and these two questions give rise to two concepts called controllability and observability. So it is necessary to understand these two questions to understand these two concepts of controllability and observability. The first question is whether I can design a controller for all the systems. Give me any system, whether I can decide this state feedback controller or whether I can get this K matrix for any system. The answer is no. For example, let me take up one system with this state matrix. Let us say 2, -3. So this eigenvalues will be -2 plus 3. Whether the system is stable? No, it is not stable because there is an eigenvalue, positive eigenvalue, the positive real part, which is going to lie on the right side, and therefore the system is unstable. It can be shown that I cannot find any K matrix for this system to make the system from unstable to stable. Okay, you can try if you want. You can try with the different combinations and see what is going to be A minus BK, see whether the eigenvalues are shifting from the right side to the left side. You cannot find. I can challenge you. So you can try. Okay, so therefore, there are systems for which you cannot design a state feedback controller. If I cannot design a state feedback controller for the system, then it means that I will not have any control over the state variables. So therefore, if I can design a state feedback controller so that I can have a control over the state variable, then that system is what we call it as controllable system. Controllable system. Okay. If I cannot design such a state feedback controller, then obviously the system, I will call it as the uncontrollable system. Now the condition whether I can design a state feedback controller so that I can make the system as controllable is what is known as controllability. Therefore, we define the controllability as if every state variable x of t of a system is controllable in finite time by some unconstrained input u of t, then the system is controllable. Please note that all the state variables in the system have to be controlled in a finite time with some unconstrained control input u of t. Okay, in that case, that system is controllable system, and this phenomena we call as controllability. The next question is whether all the state variables will be available for the state feedback. Please note, if I want to design a state feedback controller, I need to feedback all the state variables. The question is, practically, whether all these state variables will be available in the system. The answer is no. The practical problems are of twofold. One thing is, the number of states in a system may be excessive, so that cost of implementing the sensors or sensing the variables will be huge, and therefore it may not be practically possible in all the systems. And the second problem is, some of these state variables may not be accessible. For example, if you want to measure the pressure or the temperature inside a engine, it becomes a difficult task to implement sensing the variable from inside that engine. So, in many practical cases, these state variables may not be available to give as an input to this controller. So, what is the solution? Using this state space model, there may be a possibility of reconstructing this state variables using this output and the input. Please note, when I say something as the output variables are also the state variables or a combination of the state variables which could be measured. All the variables which could be measured, we call it as the output variable, and all the internal variables which change with respect to time, we call it as the state variable. So, in case if the state variables are not available for the state feedback, then what we can do is we can try to reconstruct these state variables using this output and u of t, that is input. Okay, so because this output or output variables are the variables which could be measured, I can make use of these variables, and this input is also available to me. I can try to reconstruct this state variables. Okay, so I will have a component which will take the input as y of t and this u of t as the input, and the component's output will be the state variables x of t. Okay, so I reconstruct the state variables not directly, but from the output and using this input. This is y of t and this is u of t. Using this output and the input, I reconstruct the state variables and take it as a feedback. This could be done, mathematically or using some other physical devices. This component is what I call it as the observer. I can give you a simple practical example. Take a BLDC motor. The state variables in the mechanical side are the rotational speed, angular velocity, and the rotor position. These are the two state variables. Among these two state variables, it is easy to measure the angular speed, maybe using a tacho generator or some other speed sensors. It is very comparatively. It is easier to measure the output speed, otherwise the rotor speed. So this rotor speed is a state variable, and this state variable I take it as an output because it is easily measurable. It is measurable. But what about the rotor position inside the BLDC motor? It can also be measured, but you need to have lot of provisions, and it is a bit complicated to measure the rotor position inside this BLDC motor. But this rotor position is a very important quantity in control of the BLDC motor, because rotor position has to be sensed and appropriate circuit has to be switched on. Okay, so therefore Sensing this rotor position is a very important component in a BLDC motor operation. But since it is a difficult job, what I can do is the output, that is the rotor speed, I can make use of, and I can try to reconstruct the state variable, which is this rotor position, from this output. That component which will do this job, I will call it as an observer. Okay. Now again the question is whether I can design this observer or whether I can reconstruct the state variables with the help of the y of t, u of t, and of course maybe this A, B, C, D matrices, whether I will be able to reconstruct all the state variables from the knowledge of these quantities. Again, the answer is no. Okay. Therefore, there are a few systems for which I can design an observer, and there are few systems which I cannot design an observer. So the systems for which I can design an observer, I will be calling them as observable systems. Observable. And other system, what I will call it as unobservable. This condition, whether I can design an observer for a system or not, is what we call it as observability, or it is written here, observability. So stability is whether the system is bound, the output is bound for a bounded input, that we can assess using the eigenvalues of the state matrix. Controllability is whether I can design a controller to have control over all the state variables. And observability is whether I can design an observer which can reconstruct all the state variables from the knowledge of y of t, u of t, and A, B, C, D matrices. In today's lecture, we understood about stability analysis, controllability, and observability. Stability can be assessed through the eigenvalues of the state matrix. Controllability is the condition that whether a controller can be designed to exercise control over all the state variables. Observability is the condition that whether I can design an observer to reconstruct all the state variables from the known knowledge of input and output. With this, let us conclude this lecture, and we will see how we can test whether a system will be controllable or whether a system will be observable. That we will do in the next lecture, along with doing some numerical examples. Thanks for watching.